of kilometers per second, 20 kilometers per second. These nebulae went out to about, that was an unheard of velocity. And there was a trend. And so Hubble was the right guy at the right time. The slope of this, which we'll talk about more next time, is called the Hubble constant. He was the first one to measure it, 500 kilometers per second per megaparsec. And the modern value is quite a bit smaller than that. And we'll talk about that. Also, for those of you who are experts in science, you know, in those days, velocity was measured in kilometers. Nowadays, it's measured in kilometers per second. So that was an inside baseball. Okay. Ideas and powerful instruments. And so Einstein in 1916 put forth his theory of general relativity, which then provided the interpretation of what this meant. And what's interesting is that Newton's theory of gravity, to date, it's the most successful scientific theory ever. It lasted 250 years before being overthrown by a grander theory, general relativity. Newton's theory was simply not up to describing the universe. If you tried to describe the universe, it gave you nonsensical answers. And so Einstein came along shortly before Hubble with a new theory of gravity that was powerful enough. And, oh, I love telling stories. And fortunately, it came along in 1916 because it took them about 15 years to understand the theory. And in fact, my colleague Chandrasekhar used to say that Einstein's understanding of general relativity was very primitive, which is a true statement. He had discovered a very, very powerful theory that's taken about 100 years to completely digest and understand. And I'm going to tell you about one of the things that the important thing for cosmology is that the expansion of the universe was not an explosion of things into space, it was an explosion of space itself. And, oh, I promised a one-sentence understanding of general relativity. So, time works. Space is flexible. So that's the essence of what Einstein said. Newton said that space and time were just fixed, they're there. Einstein said, no, they're dynamic. They work. So my watch keeps different time than somebody else's watch who's moving. And space is flexible. We've all gone to the museum and seen, you know, the black hole, curved space around the black hole. And a better example, a more accurate example, is the expansion of the universe, which I want to talk about. So Einstein interprets Hubble. So here we have a theory to really make the discovery understandable. So the Big Bang was not an explosion of stuff into space. It was an explosion of space with the galaxies being carried along. And so I'll talk about that. These velocities of galaxies that were measured, probably many of you know what the Doppler shift is, that something moving will have its pitch change. If the train is moving away from you, the pitch is lower. If it's moving towards you, the pitch is raised. And this is very, very different. This is the stretching of the wavelength of light due to the expansion of the universe. And I go so gaga over this that I'm going to just show you a few redshifts. And then curved space. But first, an important question, of course, the way we answer scientific questions today is by polling. So how many people, you saw that picture, how many people think we're at the center of the universe? How many people think we're not at the center of the universe? Not so many Harvard educated. So, and this is what's wonderful about nature is the answer is somewhere in between, actually. So here those are galaxies, and through the miracle of PowerPoint, I can make space expand, so I'll just blow it up, give it a different color, and blow it up again and give it a different color. And then I'm going to put all of those three images on top of one another. And so remember, blue is time one. I'm so blind, I don't know what that color is. The whitish thing is a little bit later, and the reddish one is still later. And So what I'm going to try to show you is that Hubble's interpretation of the expansion of space not only reproduces, Einstein's interpretation, not only reproduces Hubble's observations, but answers the question, are we at the center? Okay, so here we are. This is what it looks like with respect to us. And you can see that a nearby galaxy doesn't move very far, so its apparent speed is not very fast. A far-by galaxy, due to this expansion of space, moves a lot more, and so it looks like it's moving faster, so you get it. And so now, Mark pick a galaxy, any galaxy, we'll do it around another galaxy, Mark pick that galaxy. And so you see exactly the same thing. So you see the nearby galaxies are moving away from your perspective, and the galaxies that are far away are moving faster. And you would see exactly the same kind of thing that Hubble saw. You would think that you're at the center. And then, well, in Chicago, they're more experimentalists, and so we have to do this a third time to convince them. It doesn't matter which galaxy you pick. So you pick this galaxy here, and it sees the same thing. It sees all the other galaxies moving away from it, with the ones that are farther away apparently moving faster. And so every galaxy thinks it's at the center. It's just like being an undergraduate at Harvard. And this expansion of space puts everyone at the center, and of course at the beginning time, everyone was in the same place, so there's no argument. And of course, the one bad thing about this picture, somebody can ask, what about this edge of the universe? I forgot to tell you that, the universe is very big, so there is no edge. We'll come back to that. Redshift. So this is sort of an amazing thing. This is a spectrum of a galaxy, and I apologize, it's probably the most technical thing I'll do. So this is wavelength of light, from blue light to red light. And so this is just how much light there is. So this is the intensity of light. And this is the spectrum of a galaxy. And these lines either, namely their jumps down is absorption by atomic elements. And so this is a spectrum of a galaxy. And if you're an astronomer, you immediately, your eyes go on to something called the 4,000 angstrom break and the calcium H and K lines. So those are things that you recognize. And when you look at this, you're a little bit surprised because in the laboratory, those lines should be over here at 3950. And for this galaxy, they're at about 4700. And for this galaxy, they're at about 5400. And what's happened is the expansion has stretched light. The expansion has stretched, it stretches everything. So it stretched light, and there's where it should be, and it isn't. And we can notice these features. And so 1 plus the redshift is equal to the measured wavelength divided by what you would get in the laboratory. And so that for that first one, it's 4750 over 3950, 1.2. That means when the universe left, when the light left that galaxy, the universe was 1.2 times smaller. It was 1.2 times bigger today. And the other one is 1.35. And so that's the stretching effect of the expansion, is it stretches the wavelength of light. So now let's really have fun. So, 20% effect, maybe you didn't really measure it right. So I was involved in discovering the most distant galaxy. This is a Sloan Digital Sky Survey camera built by this young lady, Connie Wacosi. And she came to me very excited with this picture and said, I think we have something important. And I said, yeah, that must be important that there's an arrow on it. So that must be something you're supposed to look at. On the sky, there's an arrow pointing at that red thing. And for a brief amount of time, this was the most distant object. And about 13 billion light years away. So its redshift is 6.4. Let me just show you the spectrum. Here's the object. So the spectrum of this object is a quasar. It's a little bit different. What you see from a quasar is light emission. So it's emission from hydrogen gas, called Lyman alpha. because the wavelength for 1 alpha is 1216 angstroms, and that's in the UV. So normally you could not see that with your eyes. The expansion of the universe stretched it so that you could not see it, because now it's at about 9,000 angstroms in the infrared, where your eye cannot see it, but instruments can. So that light, that photon, had its wavelength stretched by a factor of 7.4. And it went from 2 blue to see to 2 red to see, and it tells us that the universe was 7.43 times smaller. And everybody likes, lens speed records, so, somebody's going to ask me, what's the most distant galaxy? And this is a Hubble image, and it's a very exciting science project where we use gravitational lensing, which I'll talk about next time, to see this very faint thing, whose redshift is 9.6. So the wavelength of light was stretched by a factor of 10.6. And the universe was 10.6 times smaller when the light left. And you want to know how old the universe was. So that was less than 1 billion years after the Big Bang. About 450 million years after the Big Bang. Okay, so let me take on a quick tour of the universe here, just to orient you. The solar system. That's the sun. Identifies 4 planets. That's Earth. You know the solar system. So that's kind of small potatoes. So that's where we live. So we use light as a cosmic ruler. So we measure distances by how long it takes light to go distance. So 1 billionth of a second is 1 foot. So if you really want to, screw up the census or whatever and ask you how far you are, just put, for me it's 6 billionths of a light second. In a year, light travels 10 trillion kilometers. I jumped down to a trillion because nowadays everybody knows what a trillion is. So 10 trillion kilometers in a year. 1 light year is 10 trillion kilometers. Just to give you a sense of the solar system, it's really big. The distance out to Pluto, formerly known as a planet, the object formerly known as Pluto's planet, is 5.5 light hours. The nearest star, which is Proxima Centauri, and the only reason I can pull it out here is because it's at the center of the picture, is 4 light years away, 40 trillion kilometers. 4 light years away. That's enormous, but that's small. Oh, and Freeman Dyson talked about life in the universe. It's too bad when he gave his lectures that we didn't know about. Most stars have planets. And here's a montage of planets that were discovered by the Kepler satellite. I forget, there's 1,000, and this is by the physical size. And here is the current, potentially habitable exoplanets. So we're going to find life somewhere else in the universe in the next 40 years. If you want a stock tip from me, insider trading. So just go ahead and